Good afternoon. Today, still some people coming. Today, it's my last lecture in this block of lectures. The topic of today's lecture will be data serialization, remote procedure calls, efficient communication over the network. Starting from next week, my colleague David will start the block of lectures about Java, and we will meet each other towards the end of the semester, where I will still have one lecture about virtualization. So, topic of today is serialization, but before I start with that, I have one small announcement. We are looking for students to work with us on some projects related to hardware and a bit of low-level programming and so on. If somebody here or on the stream is interested, let me know. I will tell you the details. It's normal paid contract, and you may learn some stuff about hardware and or low-level programming. Okay, let's go back to the lecture. We will start, of course, with an introduction. Then we will talk about ways how to communicate efficiently over network, starting with some not very efficient but well-known and well-established solution, then talking about blazingly fast solutions but not very flexible, and finally about something which is practically used nowadays in most or many applications, which is called data serialization frameworks. And this will be also something for that you will practice today in your homework. So let's start directly with the introduction. So we have programs, and you want the programs to communicate over the network. Or actually you want the programs to communicate. So there are actually two ways how the programs can communicate. If the programs are running on different hosts, like it's typically the case in cloud-based settings, the programs need to communicate over the network. So how this can be done? Surely you need some kind of communication protocol. Nowadays, at least in the cloud settings, this is typically TCP, or even more often today, HTTP. HTTP is like application layer used over TCP, or sometimes it can be used even over some other protocols. But let's say this is the basics. Whenever you need to communicate, you need to pass the data to the other side and vice versa. And the procedure to encoding the data which you have in local variables in a way that the other side understands them is called serialization. That's the main topic of today, how to serialize data efficiently. If you do, the advantage of serialization is that you can actually use different programming languages to work together. One program in C++ calls another program in Java, and vice versa. They can communicate with each other. And the way how is that possible is due to this serialization, and the opposite is deserialization, how they convert data structures in memory to this common format, and we will talk about that later. On top of that, typically what we implement one way or another is called remote procedure call. So typically you are sending data to the other side, to another computer, because you want the other side to do something with the data, to execute some computation or execute some procedure, and that's why it is often called remote procedure calls. And what remote procedure call is very simple. Basically, you serialize the data. one of the data could be the name of the procedure or function you want to call on the other side, and you also serialize the parameters, arguments, send the request to the other side, to the server, then wait for response. Once you receive the response, you perform the opposite step of serialization, which is deserialization. You get the result of the remote computation. So this is the basic thing. It can have several forms and several names. For example, in Java, not sure about now, but sometime in the past, a remote method invocation was a popular thing. Basically, it's the same, just different name. Nowadays, especially in the cloud settings, you have everything communicates over HTTP, and that's basically the same thing as well. You send some HTTP request, the server handles the request by executing some code and sends the response back. So all of these things, they have different names, but they mean all the same. Those are just different ways of doing the same thing. Now let's look at the other side of the spectrum. When you want to communicate on a local host, not over the network, but on a local host, because this course is primarily about like efficient software on a single computer, on a single host. So let's look how that is different or the same. So I hope that it's obvious, but if not, just mention it. If you are multiple threads running in a single process, there is actually no need to communicate to serialize, because all data structures are already in memory. They are in a memory most likely in a way that the program it is actually running understands. So there is no need to serialize the data and deserialize them. What's sufficient is that you just pass the pointers to your data structures, and you don't need to copy data, serialize, and so on. Here, in this case, what you are taking advantage of is the type system of your programming language, because the data in memory is just a pile of bytes with some structure, and what makes this pile of bytes understandable to your program is a type system. So your compiler knows that this pointer points to some data, and this is the type is the structure, so the compiler generates the code that, I don't know, one field of the data structure is an integer and it's located at this offset and so on. So here we have the compiler, which helps us to understand what the data mean. If we need to communicate on a local host between different processes, still not over the network, but between different processes, we have basically two options. Either we use sockets, socket communication, but communicate not over like TCP, but we can communicate over, either, for example, Unix socket, or we can even use TCP over the local host interface. So from this point of view, the communication between different processes on a single host does not differ from communication between different hosts. This kind of communication would be suboptimal, because if you communicate between processes, you would have to serialize the data, send them to the operating system. The operating system needs to copy them to the process of the receiving program, and the receiving program needs to deserialize them. So there is a lot of unnecessary work. If you want to have high performance communication scheme on a single host, this is typically implemented via shared memory. So if you are on Linux, the system calls like SHM Open and mmap. And if you are doing that, you can basically implement something what's called zero copy communication, where the data is actually not copied at all. The data doesn't even have to be serialized. You just write them to memory, and the other side reads them from the memory, because the memory is shared. And this, some of the data serialization frameworks that we will talk about today support or are suitable for this kind of zero copy communication, some not, but it's definitely good thing. If you care about high performance, you should also target zero copy where possible. Unfortunately, this means that your program needs to be a bit more special because while the data is in shared memory, before the other side reads the data, you should not modify them, so your program should be careful. But if you are careful, you can get pretty high performance. That's how we can deal with memory. Now, I have said that if you communicate between multiple threads, it's the type system of your programming language to help you understanding what data actually mean. If you are communicating over the network, you cannot rely on the type system of the programming language. You have to rely on something else. And this something else is like communication protocol or serialization frameworks, or how we call it. And that's what we will talk about today. So we will start with some not very efficient data serialization frameworks. Perhaps the most inefficient way to serialize data is called XML. I guess you have heard of it. Let's say you have some address book of employees of your company. You have 3 employees, John Doe, Anna Smith, and Peter Jones. If you want to serialize this information about those 3 people, you can see the serialization here. And immediately what you can see here, that this serialization is very inefficient. Just to serialize those 6 words, there is a lot of extra information, a lot of extra text. So clearly the overhead is quite high. And the overhead is both in space. To send those few names, you need to add all those tags and elements, all things around. So the space efficiency is not high, and at the same time, like serialization and deserialization efficiency is not very high, because XML parsers, at least like standard compliant XML parsers, are very complex. XML standard is very very rich. There are a lot of things that you might even know that they are existing in XML, and if the XML parser need to support it all, it's very complex, therefore quite slow. So choose XML only if you need to talk to somebody who doesn't understand anything else than XML. Otherwise, almost everything else is more efficient. The other option, which is very popular nowadays because every web browser, every programming language supports that, is JSON. So if you want to use JSON, which is JavaScript object notation, this is like the native format supported or understood by JavaScript, but nowadays almost all languages support that. As you can see, if we want to encode the same information as before, it's a bit more concise, but still the overhead is quite high because we have to repeat first name for the first time, second time, third time, last name, first time, second time, third time. So there is still some overhead, and the overhead is at least in space here. So, but given that JSON is like everywhere, it is still very popular. So let's look at how is JSON-based serialization and deserialization, how is that efficient? Let's say we are a bit crazy and we like C language, and we would like to communicate from the C language via JSON. Maybe it's not the best idea, but let's say we want to do that. So you Google a bit how to do JSON in C. You find there is a library which is called JSON C, which sounds like perfect. So let's do a small benchmark. Let's design a program. We just open a JSON file, reads that file, and then parses this JSON so that we can process the data. So very simple. There is nothing else than just reading the file and parsing the JSON. And now let's compile this program and let's let's run it. If we run this program on a, let's say, almost 50 megabyte size JSON file that I created for this benchmark, and run the program through perf, we can see that on that computer I was using back at the time, the benchmark took 3 seconds to parse this 50 megabytes file. Sounds like maybe a good thing, but if we look in more details about the statistics, we can see that those numbers here are not very nice. Specifically, we have just 1.6 instructions per cycle, given that this was a superscalar CPU which is able to execute, I don't remember, either 4 or 8 instructions per cycle. Executing just 1.5, it's not good enough. Similarly, 36% of front-end idle cycles. So front-end is the part of the CPU which is responsible from decoding the instruction, not executing but just decoding the instructions, and 30% of that part of the CPU, 30% of time this part of the CPU was idle because the execution was so slow that there was no need to decode next instruction. So it seems like it's not super efficient, but anyway, let's look at some more details where the time is spent. So you know, perfstat is just a quick thing to get some numbers. Then you can use perf record to understand more where time is spent. So if we run it on this benchmark, we can see that 20% is spent in a function JSON tokener parse x, 10% is called in memory allocation, and so on. So let's look at this JSON tokener parse x. Let's call perf report there to see like the code of the function, and let's find where in that function is the slower, or where the profiler detects the execution happens more often, where most of the time is spent there. And this is this line, this single instruction, 7% of time the profiler sampled the program here on this instruction. And if you look where this instruction is located and what it actually does, you can see that there is a while loop, and this while loop checks for spaces. So if you look a bit around into the original source code, basically you will figure out that this tries to skip over the white space in the JSON stream. So basically 7% of time in that program is spent for skipping spaces. So this sounds like quite wasteful. So what can we do about that? Maybe JSON-C is not the best library to parse JSON in C. So you Google a bit more, you find that some guy already did a benchmark of native JSON libraries. JSON-C is where it is. JSON-C, I no longer see it. At the bottom. Yes, JSON-C is here. 135 of something. So clearly this is not the most efficient libraries here. So let's look at the top. At the top is a library called RapidJSON in C++. Not sure whether nowadays this library is still at the top, but definitely it was at the top in the past. I think even nowadays it's pretty fast. So let's try running the same benchmark with that library. This is a C++ library, so it's no longer C. C++ is a bit better because it doesn't require the programmer to do a lot of things manually, because the compiler and the language can help with many things. And that's one of the reasons why this library is faster. The other reason we will see soon. So the same benchmark as before. You can see the source code here. So we open a file, we create a buffer which the library can use for reading the file. We create something which is called file read stream, which is provided by the library, specify that the buffer is there. We create a JSON document from that library, and finally we call parse stream method on that JSON document, which does basically the same what the previous library did. So now let's look at the numbers. Let's start with perf stat, and what we can see here. Instruction per cycle 2.23, which is like better, almost 2 times, 1.5 times more than before. Front-end cycles idle, just 18% instead of 30 something. Definitely better than before. Unfortunately, let me see. I look into the source code because the most important number didn't fit onto the slide, and that most important number said that the total time was 0.39 seconds. So if you remember, the total time with the C version was 3 seconds. Now we have 0.39, so it's almost 10 times faster, which is like in line with this benchmark. So it's 10 times faster. So let's look let's look where the time is spent. You do perf record, perf report. You will find that 23% of time is spent in parse string, 22% in parse value, 18% in parse number, and almost 12% skip white space. So still, it seems that even this super fast library spends about 10% of its time in skipping white space, which sounds quite useless to me. Now let's look into more detail into the code. Let's look at perf annotate, what we can see there, where the time is spent in that function. And you can see that there is some character read from the stream, and we also compare the character with backslash, and we compare the character with quotes. And here we spend 12% of time with backslash, 6% of time comparing to with quotes, which sounds again quite a lot. So not only spaces, but all these markup characters which make JSON, they are pretty inefficient to handle because we spend a lot of time in parsing. So that's definitely it is definitely worth looking for some alternatives. But before we do that, here in this code you can see something which is called rapid JSON unlikely. Does anybody have an idea what it is, what it means, rapid JSON unlikely in C or C++? If not, I will tell you. If you look into the source code of that library, you will see that this is a macro, and basically this macro translates to a function which is called __ built-in expect. If you see what this function is, you will learn that this is actually not any function. This is some kind of hint to the compiler, and this hint tells the compiler whether the condition is likely to be true or false. If you do the compiler these kinds of hint, then the compiler is better to predict where the code will execute and is able to better optimize the code because he has a clue which branch is likely and which is unlikely, and therefore can help hardware and hardware branch predictor to execute the code better. So in this library, these branch prediction hints are, at least in these places, are encoded manually. Remember at the first lecture or second lecture I told you about profile guided optimization. So if you do profile guided optimization, those hints to the compiler are given automatically based on the profiling. So this unlikely macros or built-in expect functions, this is one of the reasons why this library is that fast, because you can see that the authors spend quite a lot of time in these kind of optimizations, and these kind of optimizations can clearly help, but still it's not like it's not sufficient, or at least we can do better, because we still spend quite a lot of time in parsing those spaces, quotes, backslashes, and whatever. So what we can do better than using JSON? So if we want to be super fast, we can use what I called raw memory here. So we have some data in memory in the program. Our program works with the data in memory, so why to serialize them to JSON or XML or something else? If we have the data in memory, we can just take this memory and send it to the other side, and the other side would just read the memory and so on. So it would be super fast. There is no need for serialization, deserialization. We just need to send the memory. So in C you can have a data structure like this. If you use like sockets, you can use send and receive system calls to send this data, and it would be fast. But it would also have some problems. Some of the problems can be seen here in this picture at the right. This is how would be the layout of this data structure in memory. And you can see, if you compile this program on a 32-bit system, the layout of the data structure would be like this. This character will be stored here, then there will be some padding, because for efficient access to data structures, it is beneficial if the field in memory is aligned to the multiple of its size. So it's beneficial if 4-byte data structure starts at address which is a multiple of 4. Therefore, the compiler automatically adds these extra padding bytes so that this integer starts at this boundary. And if this is like it, usually the CPU guarantees that it can access this data in a single clock cycle. If this data is not aligned like this, it can happen that you need 2 or more clock cycles to access the same data. So that's why the compiler does this automatically. Second problem, and the second problem is that if you compile the same on a 64-bit system, this long integer here would be 64 bits. Therefore, this address needs to start at multiple of 8 bytes. Therefore, the layout of the data structure will be different in memory. So if you need to communicate between 32-bit and 64-bit computers, those computers would not understand each other. Similar problem is, nowadays, most modern CPUs use so-called little endian data ordering, but in the past, big endian was also very popular, and still there are some computers that use big endian data ordering. This means that if you store in memory some data which is composed of multiple bytes, the order of those data bytes is different. So in little endian, the least significant byte is the first and most significant byte is the last. In big endian system, which was some older ARM architectures, older ARM computers, most significant byte was first and least significant byte was the last. So again, if you communicate between little endian system and big endian system, even though they are both 32-bit, they would still not understand each other. So these are the problems. Now let's look at the solution. So one of the problem was that the size of this long int data was not the same on 32-bit or 64-bit system. The solution is don't use plain C types like int or long int, use explicitly sized types. So in C you can use int32 underscore t, and this is always 32 bits. That's simple. If you want to be compatible between different endianing, there is a header file which is called endian.h. You can use functions from that header. For example, h2le32, which is an acronym for host to little endian 32 encoding, and this function converts the data from host encoding to little endian. So before sending the data to the network, you have to convert it, or you not have to, but if you convert it to little endian and the other function does the same, little endian to h, they will understand each other. And last but not least, I have talked about this padding, that the compiler adds extra padding to this data structure. If you don't want the compiler to add this padding, you can, at least in case of GCC and Clang compilers, you can specify the attribute packed. And if you do this, the compiler will not add this padding to the data structure. Basically, the layout would look like this. There will be this flag immediately followed by this 4 bytes of data, and then immediately followed by this info bytes. So the size of this data structure with this packed attribute would be smaller. If you access the data here in the source code, you will not see the difference, but if you benchmark it, it could be that this access to this unaligned field would be slower, and you would see it in the benchmark. So if you have code like this, you can send this memory to the other side by first copying to this is like about receiving. So whenever you receive the data, you receive it to the temporary variable. Then you do the conversion of to the host endian from little endian, where it is over network. If you are on little endian architecture, this function does actually nothing, so it will be very fast. If you are on big endian architecture, this function does the conversion, swapping the bytes, and then you can work with the data. So to conclude this, this would be like very fast, but the problem of this approach is that it's inflexible. So still it's kind of a lot of work, which in this case we have done that manually. But on the other hand, it's very inflexible because if you use this kind of communication, the receiving side must know the exact format of the data. And now imagine that, for example, we need to add another field to this data structure. Whenever you do this, then it means that you have to update both server and client at the same time, because otherwise they do not understand each other. So this is another problem which makes it harder to use this kind of solution. So before we look at how to solve this more properly, one important information which you should remember: whenever you are designing some kind of communication protocol, always think about versioning the protocol. So when the client and server communicates with each other, it's useful if there is a way how the server can know which version of the client is there, because this allows you to evolve the protocol. If you need to add some field, you can just add the field, make the server update it. The server can use this version to decide whether it will read the old version of the data structure or the new version of the data structure, and then you can update the clients one after each other, for example, and your whole system will still be operational. So as I have already mentioned, doing all of this manually is quite tedious. So we have data serialization frameworks which do all these things automatically for you, and let's talk about them. One of those frameworks, which originated at 90s last century, is called Corba. It's no longer used and popular nowadays, but interestingly, it had many things right. Those serialization frameworks that I will talk about later, they always, when you read their documentation, they always mention like, yeah, we are super fast, we do this and that and so on. And they claim like that this was invented by them. And it's actually not true. Of course, those frameworks are more efficient than if you use XML or JSON, but basically all these things that they are claiming are new. They were already implemented in Corba in 90s, and there is not many new things in them. So very briefly, everything about these new frameworks is very similar to what was there in Corba. So for example, there was something which was called interface description language. Nowadays all those frameworks use something like that. Maybe they don't call it IDL, they call it scheme or whatever, but still it's still the same. Then there are some like automatically generated codes that handle this communication, serialization, deserialization, and so on. So, for example, in Corba, if you want to communicate some information about accounts, you define your data structures in this interface description language. It could look like this. So you can see there is a structure. It has some string, long, double values, or whatever. It looks like a structure in C or similar. And then you can use idle compiler to generate C or C++ or Java or Python or whatever data structure or whatever programming language to work with this data structure. So this way you have one canonical definition of the data structure, which then gets translated to different programming languages. The other feature introduced by Corba is so-called common data representation, and that's this quite efficient serialization format which almost or many of the new serialization framework implement in one way or another, even though they call it differently. And there is few features which are notable, which all efficient synchronization schemes somehow implement. So endianing, how to deal with endianing. What Corba did, they decided, let's not convert the endianing by default, let's use the endianing of the sending side, because often it's the case that both sending and receiving side use the same endianing, so it's useless to convert it to previously what was used like big endian was the network order. So whatever you sent to network, the rule was converted to big endian. Nowadays everything is everything is little endian, so it would be inefficient to convert it to big endian and back. So Corba said no conversion, we are always sending in native endian, and in the header of every message there is one bit saying which kind of endian this is. If the receiver uses the same endian, there is no need for conversion. If the receiver if the receiver uses different, and then it needs to convert. And the second feature of Corba is that data padding in the messages sent over the network is the same as what would the C compiler do in memory. So all fields are, which is called naturally aligned. So 4-byte fields are aligned to 4 bytes, 8-byte fields are aligned to 8-byte addresses, and so on. By following those two rules, basically the serialization of data in Corba often can be implemented just memcopy, similarly as we did before. We just need to prepend a header to every message, and we are done. Another feature supported by Corba and also by some today's system. In Corba it was called type codes, which was a data structure describing the structure of data to be sent. So this way, by using those type codes, it was possible that two programs communicate each with the other in a way that they didn't know what is the content of the data, because if the program first sends the type codes, then the other side understands how to decode the data, how to create objects, and so on. So this was used in Corba as well. Nowadays, the serialization framework use it, even though they call it typically differently than type codes. They call it schemes or something else. Okay, so we know the basics, we know the history, and now let's look at few reinvented wheels. First reinvented wheel after Corba is protocol buffers. Protocol buffers is an older, I would call it older serialization framework, which was made popular because it was released by Google. It's not nowadays, it's not the fastest, but yeah, but it's still faster than JSON and has some better properties than JSON, because it allows kind of versioning the data natively. So let's look at how Google Protocol buffers, or protobuf in short, what it actually is and how we can use it, because this would be one thing that you will implement in today's homework for comparison. So similarly to Corba idle, you describe your data in some kind of language. Here that language is called proto language or proto definition, and it looks like this. You define not structures, but you define messages, but in case of C this is actually translated to structure or to C++, and you define some fields of that message or structure. So there is one field called query, another two fields are page number and results per page, which are 32-bit integers. What's interesting is this equal sign here and the number. So don't confuse those equal sign and numbers for default values. These are not default values. This equal sign is just a special syntax for assigning what's called a tag. And here the thing is that every field has a tag which somehow identifies the field. Those tags are used to encode like which kind of field is there. So if you are sending the data in JSON, you always put the name of the field in the JSON, like query, and it's string. And it's, for example, here it would be, I don't know, 10 or 12 bytes, or how long that is long. In protocol buffers, you identify the fields with this tag, And as you will see, in the simplest case, sending or transmitting the tag requires just 1 byte. So it's quite efficient space-wise to identify which field is there. And another advantage of using those tags is that it allows, or it simplifies, versioning of the protocol. So for example, if you add a field here, you add new field to this data structure, it will be given new number 4, and on the receiving side you can always ask, is there field number 4 in this data structure? If yes, then I know this is a new version. If not, I know this is the old version, and it works. Similarly, if you want to change the type, for example, if you want to change the type of result per page from 32-bit to 64-bit, you can do it, but then you should also change the tag so that the receiving side know whether the client sends the old 32-bit version with tag 3 or the new 64-bit version with tag 4. So this is how protocol buffers helps with versioning. Now let's look a bit more into detail how the serialization format actually looks like. It's called wire encoding, how this data structure gets encoded to the wire, to the lowest level, into sequence of bytes which get translated. So everything sent via the protocol buffers is sent as a key and value pair. The key is a number which specifies two bits of information. The first piece of information is the tag, which we have just talked about, and the second bit of information is type of the data. Protocol buffers define six types of data. The first one is so-called var_int, and we will talk about it on the next slide. Var_int encoding is used for encoding most integer types like 64-bit, 32-bit signed, unsigned, Boolean, or enumerators. Another type of encoding is 64-bit encoding, which is used for floating point numbers. Then length delimited encoding is used for strings and embedded messages, embedded structures, and then you have some others which are not used that often. So whenever you want to send some data, you first send this key, and this key is a number. You take the field number, which is basically the tag, shift it to the left by 3 bits. And the lower 3 bits store the type according to this table. So this is pretty quick operation. Both logical OR and logical shift, those are operations which CPUs can do very quickly. Most likely all of them can be computed in a single clock cycle. So doing this kind of computation doesn't slow down almost anything. So now, how is this key stored, and how are all the other integer numbers stored? These are stored as so-called var_int type. And what does it mean? When talking about those tags, at least in the example you have seen, the tag is pretty small number, typically 1, 2, 3, 4, 5, and so on. So it would be wasteful to, for example, always use 32 bits to send those small numbers. Therefore, in Google they decided that they will encode those var_int numbers as a variable number of bytes, and that in every byte, 7th bit, meaning the highest bit, will equal to 1 if it is not the last byte of this encoding, and there will be 0 only in the last byte of this encoding, and then the remaining 7 bits in that byte will just store the number. So if you want to send or encode this number 9 as var-int, in binary 9 is encoded as 1001. This can fit into 1 byte, so this is encoded as 0, as like last byte of that number, and then 1001 bits here. This is easy. Now let's say we want to encode a number 300. 300 is decoded into binary as 9 bits, so 1001 and so on. You cannot send 9 bits in a single byte, and so we have to split it into 2 bytes, because in this var-int encoding 1 byte can carry only 7 bits of values. So we take the lower 7 bits, which are these, not sure that you are seeing it, but these are in blue. You take those 7 blue bits, put them here, and put 1 as this indicator bit, which indicates this is not the last byte. And then you take those green bits, the remaining 2 bits which are here, you put them here, and complete them with 0 7th byte, meaning that this is the last byte. So as you can see, this is still pretty efficient. This number which cannot fit into 1 byte is still encoded into 2 bytes here, and therefore the overhead compared to binary representation is not that high. Of course, there is this overhead of 1/8 of bits, but it's like acceptable, let's say, at least for the use case they had in Google. So this is how you can encode positive numbers. Now, how to encode negative numbers? If you know how negative numbers are represented in computer memory, typically it's 2's complement, meaning that -1 is encoded like as FFFF or all ones. So if you would need to encode this all ones, let's say 32-bit all ones, it would be very inefficient, because you would need to encode all, like, let's say 4 bytes or all 32 bits, and every negative number would, every negative number would take quite long big amount of bytes to encode. So instead they decided that they will translate side numbers this way, that they will not use the highest bit to denote the sign, but they will use just the lowest bit as a sign marker. This means, or this can be calculated pretty efficiently in C. You just shift the number 1 bit to the left and perform XOR operation with the same number shift by 32 1 bits to the right. This is how you how you move the sign bit from the most significant bit to the least significant bit. And the result is that if you have small positive or negative numbers, they both result in small positive number after this encoding. So -1 is encoded as 1, +1 is encoded as 2, and so on. If you see that this goes like zigzag, 0, -1, 1, 2, -2, 2, -3, 3, and so on. So this is just jumping here and there, and this results in consecutively increasing numbers here. This way, basically, small numbers in absolute value encode into a small number of bytes, and this is usually what you want in many applications. So this is how those var-ints are encoded. These are used for keys, and these are also used for integers. And now the last important data type in protocol buffers is string and messages, and these get encoded as first we specify the length of the message, again as a var-int, and then the amount of data in the string or a message. So for example, if you have a message containing one string with tag 6, this get encoded as 32. 32 is the tag shift by 3 bytes, ORed with 2, which stands for this var-int encoded. So this is the key, and the value again is var-int here. 7 is the length of the string. Because it's less than 7 bits, we don't have to change that value, so it's just the length of the string. And then these are ASCII values of the string testing here. So as you can see, sending this message is pretty efficient. Basically, there is just 2 bytes overhead over that. If you compare that to JSON, the overhead would be much higher. Here we have another example. Now protocol buffers support something which is called repeated fields. Basically, this is a way how to encode arrays. Question?
Does it mean that the maximum length is 256?
No, because this length is var-int encoded. So whatever can be encoded into var-int can be there, and if you go back, all this can be encoded as var-int, so unsigned integer 64. So you can have all your memory can be one string, and it will fit there. The advantage is if you have short string, you need just 1 byte for the length. If you have long string, you can have more bytes for the length. So short strings are encoded efficiently. Longer things are not so efficient, but because the string is much longer, this efficiency doesn't pay or doesn't make big difference here. Yeah. So repeated fields. This is a way how protocol buffers can support arrays. Arrays are again variable-sized arrays. If you don't know how much numbers you will have, you can specify it as a repeated int 32, and again this is encoded as with a tag. Then there is the number of elements in that array, and then var-int encoded elements of the array. And as you can see here, some of those elements which are small are encoded as 1 byte. Elements which are bigger, like this one, are encoded as 2 bytes. Even bigger numbers are encoded as 3 bytes. So space-wise, this is quite efficient. I will show you an example here. If you have ever worked with OpenStreetMap, you can download the data from OpenStreetMap in various formats. One of those formats is also protocol buffer format, and the other one, at least when I tried it, was XML. And here you can see the comparison of the size of the map of the Czech Republic when you download it in XML or protocol buffer. So XML was 16 gigabytes, protocol buffers was 670 megabytes, which is significantly smaller. This is the definition what is the data structure of OpenStreetMap data. Basically everything is encoded as a node, where node is defined by latitude, longitude, and then it has some keys and values like there you can store whether this is a road, whether this is a I don't know, wood, whether this is a river or whatever. This can be stored here, and there is an ID of that node. And then you can connect those nodes by so-called ways. Those are those lines here, and every way has an ID, of course, and then it has keys and values, and finally it has this repeated references, and those references are basically the IDs of nodes of the way, and this is so-called delta coded, which means that these are not absolute numbers like ID 1028 or whatever, but these are only the first one is absolute, and the subsequent are just the difference from the previous one. So in many cases, if you have situation like this, in many cases those node numbers are consecutive. So 42 is followed by 43. And if this is the case, then this delta encoding means that this ID here is just one, and because it's just one, it can be efficiently stored as 1 byte var int. If you specify absolute numbers, and those numbers would not be like 42, but let's say 4200 and 4300, you would need more bytes to store these numbers. But even though if you use this delta encoding, it would be still just 1 byte. So this is why it is useful to understand like the lower the format of the data, because you can optimize your data so that they can be encoded efficiently and consume much less space there. And if something is smaller, you know it's faster because you can fit more data into the cache and so on. One more thing related to using protocol buffers and similar data serialization frameworks, at least for your homework today. Originally, these were not designed for communication over the network. So these serialization frameworks were designed for storing data to disk. If you want to use it for communication, especially over TCP, you need to add so-called framing. Meaning that before you send the data, you should send also the size of the message, so that the receiving side knows how much data it has to wait before processing the message. If you don't do that, and you should already know why this is needed, because if you use TCP, as you did for your EPOL implementation, it can happen that a single message is split over the network by some routers, switches, or whoever into multiple packets. So if you don't know what is the size of the full message, you don't know whether you have received the message or multiple messages and so on. So for this reason, it's necessary to just put some data information about what is the size of the message, and only then you can send the message. I'm mentioning that because this is what you will need to implement in your homework. And This is not provided, at least in C++ implementation of protocol buffers. You would have to implement it yourself. Now, if you want to use protocol buffers in your code, how you can do this. So, similarly to Corba, you define your data structures that you want to use protocol buffers with in a file which is called something.proto. So for example, you define a person which has a name, which has an ID, which has an email, and then you can define address book, which is a repeated number of persons. So basically, it's an array of persons. Then you invoke so-called protocol buffer compiler. This protocol buffer compiler then generates C or Java or Python or I don't know, whatever language you want source code. And then you can, in case of C++, you can include this automatically generated source code to your program. So I'm not sure you are seeing it. Hopefully you have good eyes. So maybe I can just zoom it. Let's see. Might be a bit better. So you include that automatically generated file. This defines several types like address book, person, so you don't have to define them yourself. They are already defined in the protobuf definition. And then you can work with those data types as with other objects. There are methods on those types which you can call. So for example, you can ask how many persons is there, so that you can iterate over all persons. You can check, you can read the name of the person. You can ask whether there is an email or not, because in the definition the email was optional and so on. So it is then quite straightforward to either read the data or even to generate the data and serialize them. Yeah, so this is how you can work with the data. Also, there is a function which is called, I don't know, serialize and deserialize, which allows you to convert this data structure to the serialized form or vice versa. So this is about protocol buffers. Now. Protocol buffers, as I mentioned, this is already quite old, and nowadays it's not that popular as it was 10 years ago. Nowadays there are more popular things. So I will mention just 2 or maybe 3 of them. One of them is called Cap and Proto. Interestingly, Cap and Proto was designed by the same guy after he left Google. So it's inspired by experience from protocol buffers, but let's say he tried to solve the drawbacks of protocol buffers. One of the drawbacks was that you have to always use serialization, deserialization, which slows things down a bit. The key feature of Cap and Proto is that this is very efficient for shared memory communication, because in case of shared memory, you don't need to do the serialization, deserialization, because the data structure, how is that laid out in memory, is actually the same as it would, or similar as it would be layout naturally in a C compiler data structure. But there is some kind of optimization behind the scene, so therefore it's still usable over the network and so on. So for this reason, yeah, Cap and Proto, for certain application, it's very, very efficient. It can be almost as fast as this raw memory thing that I have mentioned before. So very briefly, let's look at how Cap and Proto works. I don't want to go into the details and explain everything, but I want you to see like the key differences in the architecture and maybe some tricks which allows to make it more efficient, so that you know what these tricks are and you can apply them in your code if you need them. For example, if you don't want to use cap and proto, but you need to use something else. So one of the trick is that whenever you have a Boolean value, this is actually encoded as 1 bit, and multiple Booleans can be put together to a single byte or single integer. So there is some kind of compression of Boolean values. For integers, they don't use this var_int encoding because this var_int encoding was space efficient, but you always need to do this encoding, decoding, and it was not that fast as was needed for some applications. So they store integers in memory just as they are, including all the padding. So that's why it is suitable for shared memory communication. Another interesting feature is how they encode default values. So in protocol buffers, there was nothing like default values. Here they have default values. If a field has a default value, this is encoded by taking the value and performing the XOR exclusive OR operation with the default value. Why? This means that whenever you are sending the default value, this default value gets encoded as 0, because whenever you XOR one value with the same value, the result is 0. And thanks to the other feature, which is called packing, which is optional, this packing allows to get rid of all zeros. So if you want to have a small data size, you can enable this packing. Then you need to wait a bit with encoding to perform this packing, but the size is small, and for those default values, all those default values can be packed very efficiently. So let's look at this packing. Given that all the integers are stored natively, so if you have like 32-bit integer, it's like 4 bytes. Even if this 4-byte integer is very small number, like 1, 2, 3 or something like that, it is still stored as 4 bytes, and the space efficiency is not very high. So optional packing basically allows to getting rid of all zeros, not only those zeros from the default encoding, but all zeros, even from normal integers if they are small. And it works like this, that there is always the first byte which indicates every bit in that byte indicates which bytes were 0 and which not. So for example, if you have data, there is 8 0 0 0 3 0 2 0 0. Here we need to encode only the non-zero bytes, like 8, 3, and 2. And in this byte, the single bits in this byte define what is the index, which position where there is this 8, 3, and 2. So this 1 indicates like this 8, and 5 are 2 bits for 3, and 2. And the same for the other part of the code. So if you have 8 zeros, this get encoded as a single byte. If you have few non-zeros byte, the non-zero bytes are here, and 1 additional byte extra is stored there. So this is for integers and for this optional packing. And now perhaps the most interesting thing is how structures are encoded. And they encode structures by using so-called pointers, but these are not pointers in the like C sense. They are pointers, basically offsets in the data structure, and it allows to it defines where the data structure is, where the individual fields are, and what it also allows is that you can always skip the data if you are not interested in them. Or if you are not either interested or if you are not if you don't know, for example, the type, you can just skip it. You don't have to decode everything, and you can skip it. So here is an example. Again, we have this person similar as before. This person, the syntax of this definition is a bit different. The tag is not specified with equal sign. The tag is specified with @ and you have the type like here. So this is the definition. And now if you have a single message called person, there is 8 bytes of the pointer which defines like the length of the data. And from this information you can see that this green thing here is actually the message. If you are not interested, you can just skip it and continue what would be here, perhaps next person or something else. If you are interested, you know that there is an offset 0, so you know that the field here starts here, and you can start parsing. There is another pointer which somehow specify that certain fields are there, and then you can just go one by one, and what you figure out that basically this data structure, as it is defined here, forms some kind of tree structure also in memory. So this is very efficient. If you have this data in memory and you just want to read a single, I don't know, like phone number or whatever, you don't need to read everything. You can just follow those pointers, only those pointers that you just need, and very efficiently reach the data that you are interested in reading. So this is I think how this encoding would look like if you don't use this packing. As you can see, there is a lot of zeros, and if you use this packing, you can get rid of 83 zeros and add 17 bytes more, so it's still pretty efficient. If you want to use CAP and proto, so the basic trick or the basic procedure is the same as with protocol buffers. You define this CAP NP file, which defines the structure. It gets compiled by the CAP and proto compiler, and then similarly as before, it generates this address book capnp.h, which you can include in your program, and then do basically the same as before. Iterate over the person, ask which kind of address it is, whether it has an email, and so on and so on. So this is about protocol buffers, about CAP and proto. Now nowadays protocol buffers are not popular. CAP and proto, I'm not sure about the popularity, but given that the guy has left Google, it's I think not that much popular, even though it's pretty fast. In Google, they have developed something similar, which is now quite popular. It's called flat buffers. So it's kind of follower to this protocol buffers. It uses basically many tricks from the CAP and proto. Some tricks are the same, some tricks are different. There are some advantages, disadvantages. Basically, all of those technologies are faster than original protocol buffers, and seems that flat buffers are more popular. Last thing that I want to cover today, but just very briefly, is Apache Avro. Personally, I have never used it, but it's a popular thing of the other teacher, David Šišlák, and that's why you will use it for today's homework. The goal of today's homework will be to implement communication between C++ and Java, and you will try to do it via JSON, protocol buffers, and Apache Avro. So very briefly what it is. Yeah, it's serialization framework, but it has few differences from protocol buffers, CAP and proto and so on. So one difference is that it doesn't have a special language to defining data structures. The data structure of the communication is called scheme here, and it's defined via JSON format. So instead of having .proto, you have some JSON file which defines the content of data. Whenever two programs connect to each other, they can exchange those schemes between each other, so that at connection time the client and server can understand whether there are some differences, whether the client has old version of this data structure or new version, and so on. And because it's popular in Java, the server, for example, can automatically generate code which gets recompiled by Java compiler, and it can do very efficient conversion from the old data structure to the new data structure, and so on. So this scheme handshake after the connection establishment, it slows down like connection establishment, but once the connection is established, the sending and translation of data between different versions can be very efficient. The other advantage of doing this scheme handshake is that there are no tags or anything, any information to identify which field is which field, because all this was already given in the handshake. So during the communication, the programs actually transfer only the data. At the beginning, this is just this message. This is a person in address book, and then there are raw data of the person in address book, which is kind of similar to what would you if you just copy raw memory from your program, because the compiler already knows that this pointer points to a person or address book. And last but not least, Avro supports compression. There are some interesting compression techniques like per field compression and so on, which allows to gain some significant storage size. Because, for example, if you compress the data not as a single big file, but if you compress just column-wise, like you compress all phone numbers for all persons in the address book, the compression is much better than if you compress together phone numbers, names, addresses, and I don't know, whatever. So this is this feature, and also the way how the compression is implemented is that it allows to deserialize the data even without decompressing them. So if you need to read some data and you are not interested in phone numbers, those phone numbers don't have to be decompressed, and you can read the rest without decompressing the data, which results in pretty interesting speed in these cases. So that's all for today. So to conclude, I will just repeat the main things. Whenever you need to communicate between different programs, you can choose from a big number of options. Some options are good because, for example, they are human readable, like JSON, but typically this means that they are also slow. There are different serialization frameworks. It's useful to understand what they actually, how they are implemented, what they offer, because there is no one size fits all. One framework can be better in one case, another in another case, and you should select the right one. So unless there are questions, which it doesn't seem, then thank you for your attention, and next week you will see David Šišlák starting talking about Java.